Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering as a hobby. So here is our little fancy power brick thing, and I want to talk about the some of the technical stuff with it. And to do that, we're going to open it up. It's not going to show us too much because uh, opening it up shows us this little piece, but this is still kind of behind this slightly annoying frosted glass. And I don't think there's a way, an easy way for me. Um, yeah, this feels like it's gonna break. So I think I'm not gonna screw with that. But we can still look at what's inside. So let's walk through what's actually here. So we've got this red lead, right? This is our red lead. It's gonna go in through here. It's along the edge of here and it connects to this little metal guy. This is where the positive end, it's hard to see, but you can see there's like a little plus here. So it connects to the positive end of the battery. And here's the negative end of the battery, which connects to this spring. The spring, if you're ever curious, the spring is always the negative end of the battery. This is literally just a metal sheet. So these two things are directly connected. It's just, I don't know if you can see it, but it's just a metal sheet. So this is the positive end of the second battery, which connects to the negative end here, which again, this is just a sheet. This is the positive end that connects here to the negative side of this battery, and then this connects to the switch and continues going. What that effectively does is it lays three batteries end for end, right? So we basically have three batteries that look like this, but these are connected and these are connected. So it's essentially the same as doing this, where they're connected end for end like that. Now, a battery is just going to be 1.5 volts. That's just what a AA battery is going to be. So what we essentially have now is we have a battery here, a battery here, a battery here. Each of these at 1.5 volts, and they're connected like this. The technical term for this is series. They're connected in series. That means that they're just connected end to end like this. And what that does when connected in series is it adds the voltages together so that total we get 4.5 volts. That means coming out of the positive here, we have 4.5 volts right here. And this is our red lead. Coming out the other side, we go somewhere else. Now let's look at these batteries for a second. Rather than just taking my word for it, let's actually prove what I just said. So I'm going to create, this is a multimeter. This just measures voltage, current, whatever I want. And this is a battery. And so if I connect these here, this is going to measure the voltage. I'm going to get 1.66 volts. That's about what I expect for a battery. It's a bit higher when it's relatively charged. It's going to go lower as it drops, but it'll be somewhere between 1.4-ish and 1.7-ish, especially for non-chargeable batteries. If I connect a bunch of them like this, and I'll kind of use this as a little bolster. This is going to be slightly wonky, but let's see if I can make this happen. So we'll connect all of these guys like this, and we'll kind of do this. What do I get? 4.7. So there we go. So what that's doing is it's giving us our power supply. We're going to have a 4.5-ish volt power supply. Now coming from here, we have the switch. So we can see that right here. Here's the negative side of the battery coming to the switch, which connects from here to here. From there, that connects to this yellow guy. On the outside of the yellow guy comes out to this black lead. So what's the yellow guy? Basically it does this. And then this is our black lead, which we say is connected to ground. So we have this big question mark. What is this? When I first saw this, when I just glanced at it, I was like, okay, there's a capacitor here. I thought they were doing a filter capacitor. That was my guess. Commonly, you have some setup, like if I were to redraw this in a kind of tiny way, you might have something like this, where you have a capacitor, and then over here you'd have some, there we go, some switch. This is what I originally thought it was going to be. So here's our plus 4.5, and here's our ground. And this capacitor acts as a sort of filter. You don't often see this in like pure battery circuits, but it's not super uncommon, especially if we expect sort of variations of things to happen, because it can keep the voltage steady. That's kind of its job as a filter. This is what I thought was going on, but that is clearly not what's going on. We can see that it is not connected that way. It is connected very much in series. So it can't be a capacitor, or else this would not work. You would get no current flow because it's not going to flow through a capacitor. So what do we actually have here? What is this? Well, you can't see it. I was able to look at it under a little magnifier and kind of through, like, this is all frosted, but this tiny little piece here is clear, so I could kind of go through here. I don't think you're going to be cool enough to show on camera. No, there's no way. Yeah, it doesn't know what to focus on. Nope. Okay. So, but I was able to actually look up what it is. So let's take a look. It is a 72 volt, 500 milliamp resettable fuse. So it's a fuse. It's a fuse that works. There's a material inside that as it gets warmer, as more current flows through it, it gets warmer. And as it gets warmer, it's going to the current is going to, sorry, the resistance is going to go way up. So once it reaches a particular threshold, which is 1 amp, that's its trip current, then it will basically trip and block off. Its max current is 500 milliamps. I think it's going to start declining at that point, but we'll find out. So yeah, it's a resettable fuse. These are not uncommon. It's just a fuse, except it resets once it cools down. So what we're going to do is we're going to see what happens. So back here on the bench, we're going to do the incredibly ill-advised thing, and don't do this at home. This is definitely not what you should be doing. I did actually go to school for this. Not that that really means anything, but don't try this at home and don't sue me. So here we are. We'll keep this on. Okay, so this is, all I've done is I basically connected this circuit. I've just shorted this out. Okay, now that we have everything set up, we can come here to the power supply. This is a close-up of the power supply. We're on channel 2, so this column is the one to look at. I've set it to 4.5 volts, and I've set it to 0.1 amps. So 4.5 volts is our supply, and 0.1 amps is well below the 0.5 that we're looking for. These two values are what's actually happening. This is the voltage and the current that's actually going through the component right now, through the power supply right now, which of course is 0 because I have it turned off. So what I'm going to do is I'm going to turn it on. Now these power supplies can function in 2 different modes. So if I turn this on, there is this light down here, and you see CV in green and CC in red. CV means constant voltage. CC means constant current. So it can either say, I'm going to set this voltage, like act like a battery, I'm going to set this voltage to this thing, or it's going to say, I'm going to pump out this current. Basically, how it does this is it will see these 2 values that I've set, and it will not allow me to go above either of those values. So if it tries to do too much current, it'll lower the voltage to make sure that it's okay. It's all a bunch of technical stuff, but suffice it to say, I am pumping right now 0.1 amps through that circuit that we just did and through that little fuse. I'm going to tweak this now. I'm going to press this little waveform button. Oh, wrong one. Let's go to the correct one. Waveform button. Here we are. So you can see this, like, it says this tiny little green line. This green line is our 0.1 amps. So I'm going to start raising this value. I just raised it to 0.2, and you can see it bump up just a little bit right there. I'm going to raise it to 0.3, 0.4, 0.5. So here's our limit. This is meant to be our current limit. So we're right at that limit right now, and we're going at 0.5. Let's go to 0.6, 0.7, 0.8, 0.9. We're still going. We're now at an amp. This is a full amp. This is where it should be cutting off. I'm watching the voltage rise. That's this yellow line. Oh, and it spiked. There it went. That was the crossover. So I'm going to turn off the power supply so we can look at this. That's an interesting thing. So there's a yellow line that's almost impossible to see because it was so low. That was very, very low here. And it cranked up. You can see this yellow line kind of go up here, and then it stayed constant at 4.5 as this green line just plummeted down. That was our crossover. That's when the heat of the device got to be so much that it basically flipped out. If I drop this back to 0.5 and turn this back on, we're actually fine again. We spike back up, our green line spikes back up, our yellow line's hard to see here is down. If I crank this back up, notice that when I hit 1 amp, it takes a while. So here's our spike of 1 amp. We're watching our voltage climb, 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 and then we see it spike and we see the crossover right there. So that is one of the disadvantages. I'm going to shut this out. One of the disadvantages of this kind of a system over a regular fuse is it took a few seconds, right? It took a little bit, but it's resettable. So if I crank this back down to something more reasonable, like 0.3, and I turn it back on, I'm at 0.3. I'll turn off the waveform and we can see I'm sitting at 0.3, no problems at all. It's going to sit here. It's going to be fairly stable here. This voltage is not freaking out. So we're going to be stable here at 0.3. No issues at all. If I go to 0.6, I might be stable here. It says it trips at 1 amp. It seems like it's not tripping here. So I do appear to be stable here as well. And yeah, but as soon as I start going up here, look, I'm at 1.2 now, and boom, it just collapses back to our waveform display. We can see it happening again. But my current was way up there. And that is a problem. That does become an issue. And so, you don't want this where a surge can really damage your components. If a surge, like a spike, can really damage your components, this isn't going to work. It's not going to be a great solution because you're going to fry the component before it actually trips. But for something like what we have, like our little motor guy here, going over current for a second, unless you're way over, is probably not going to be too bad on this. It's not going to be great, but it's probably not going to be too bad on our little motor here. So I think it's a good solution for this specific power supply, especially for what this is a hobbyist, like, someone's gonna screw this up. That person is gonna be me for sure. But one important thing about motors in general is that they have what's called a stall current. So if I just took a pair of pliers and just held this, like I just forced this to not move, it's going to draw more current than in any other circumstance. It's called the stall current. And usually, you need to account for that. And so it's like a quick stall, it's not really going to do much, but sitting at stalled for a long time could damage stuff. And so this is a really good way of ensuring the circuit maintains integrity, that if I do stall for a long time, it just shuts down, then comes back up when it cools off. And it's all done with cooling, or with heat. So as this little yellow guy here heats up, its resistance rises significantly. causing the current to plummet. So very cool. That's it for the technical video. Thanks so much for watching.